This
So,
conference will now be recorded.
all right. So thanks everybody for coming today. I'm really excited to be talking with you. I'm coming to you from Los Angeles, where we think it's cold at 68 degrees, but I know it's a lot different for you. So this is part of the Distinguished Lecture Program. So we just encourage the chapters to give us feedback. It helps me improve our presentations, and then the folks who run the Distinguished Lecture Program appreciate the feedback as well. They're always asking us to reinforce that Ashrae is a volunteer organization, so wherever you might be able to find a way to plug in to help us move forward, please consider it. So today, what we're really going to be looking at is holistic approaches to multidisciplinary design. Obviously, we're mechanical engineers, but we're part of a much larger ecosystem of design, construction, manufacturing professionals that help to support projects that are far more than mechanical engineering. And so part of what we need to do is understand the unconscious bias that's built into our professional worldview, start to build collaborative techniques to build design empathy, and then understand the design sensibilities of our partners outside of HVAC engineering. So the place I like to start today is something I call defragging design. And I was always struck when I saw this diagram in a book that I was reading about multidisciplinary approaches, that the traditional paradigm of procurement starts by having gaps that inevitably occur in between the different disciplines, right? And then there's gaps that seem to occur as we go phase by phase by phase, that you don't always have the same team, you don't always have the same parties, and things that people are carrying around in their heads sometimes don't make it onto drawings or specifications, or they're not super documented, or that guy stored everything on his C drive, and so by the time you inherited it, it's like, what was he thinking? That by the end of it, you sort of end up with these sort of operational islands, right? Where through either poor coordination or poor communication, you end up with these gaps that you end up finding out about a little bit too late. And so the question is, how can we look at our design process and see about how to kind of reduce some of those gaps? Now, we've had the promise of integrated project delivery, right? That there's been a lot of proposals there about having contractors and designers like working together very, very closely at the early part of a project, where they're able to set their priorities, and hopefully we avoid any sort of adversarial relationships, because people have built relationships at the part, and the financial structures of these organizations are such that everybody succeeds financially if the project succeeds in delivering what the client needs. And it's sort of meant to encourage their mutual collaboration. And what we've always struggled with, there's the old PM kind of joke that between looking at getting a project fast, getting a project good, or getting a project cheap, you can usually get 2 out of 3, but it's super hard to get all 3 at the same time, right? And so how do these new integrated project deliveries help to get faster feedback about what can be good and lower cost that doesn't adversely affect schedule or vice versa, right? And really balancing the priorities is the key. And so, I know you all have experience with this. The traditional design process has those contractors coming super late. The integrated design process has the contractors integrated earlier. And so kind of what are those benefits? How do we make sure that we get the best out of everyone's expertise? And it has to do with when decisions are made and how they're made, right? So you might be familiar with this sort of curve, which is called the McConahey curve. And it was created by an architect at HOK. And he said, hey, look at the line, which is number 1, the blue line, right? Your ability to impact the cost or functional capabilities on a project reduces the later you get in your phases. And then you look at, number 2, the red line, the cost of making any change gets more and more and more expensive. And we all know how expensive it costs to change anything during construction, right? And so the traditional design process kind of put all the sort of all of the key efforts on the design team at sort of that detailed documentation at CD stage. And a lot of times, you know, we weren't getting the decisions that we needed earlier on, because a lot of times I think our owners and their stakeholders, like, they can't envision things in their head until it's super close to construction, right? And then they start making all these decisions. It's like, we asked you all these questions like 5 months ago. Where is this coming from? And so part of the preferred design process is to kind of move some of that lump from CDs, construction documents, backwards in the phases or upstream in the phases, so that we can get into that sweet spot where you can still have relatively high capability of making design decisions, but still at relatively low cost. And now we have tools that allow us to kind of sort of optioneer in that way in a digital space, as opposed to it having to be grounded in physical space. And so that's where the promise of building information modeling has come in, right? Where we have these sort of real-time updates of 3D models, so-called virtual design and construction. You're able to kind of visualize what everybody's doing. And even if you don't have a single model, because, you know, most people aren't working in single models because they just get too giant, but having a common platform, you know, that allows everybody to see the same thing, allows people to share and extract data from each other on a faster basis from that common platform. And we all, you know, and every discipline can draw on these platforms, embed information in these platforms. But the thing that I always remind our younger engineers is, who are very digitally capable, they're digital natives, they want to get straight into the model. And I always try to explain to them that BIM tools are only there to capture our thoughts, right? The models are the artifacts of our thoughts, in the same way as, you know, when ancient cave people would leave artifacts for us that we find when we do archaeology. Those were tools to do a task, right? And BIM is a tool to do a task. It is not design itself. It's a representation of our thoughts. And sometimes it's not a fully complete representation of our thoughts. And so we always have to question what information is appropriately held in a BIM model and what supplemental information needs to be passed on to get everything out of our heads, so that we don't have those gaps that we looked at on that first slide, right? And so part of that is also understanding sort of this aspect of design empathy, right? There are things and blinders that we are taught in our education, right? Every discipline is trained to see the world differently. We're trained to understand heat transfer and flows, whether they are flows of fluids or flows of energy, right? We see the world in the way things move. Our structural engineer colleagues see the world in the way to make things not move, right? Because movement is dangerous in most cases. Our electrical engineering colleagues work at an understanding at a super teeny tiny scale of understanding where electrons go, that I have no clue how any of that works, despite frying, you know, circuit board after circuit board in my one electrical engineering class that I took in college. I don't understand it. I just trust them that they're keeping us all safe. But that training that we're taught in college, and that's reinforced through communities such as ours, to develop knowledge, to develop research, to share information with each other, makes us super expert, but with blinders on sometimes. And so we have to ask ourselves the question, right? There's this great quote, you know, an architect's dream is an engineer's nightmare. But for whom are we the cause of nightmares, right? And what is it that we do? And that, you know, building that sort of design empathy is a big part of being sort of a professional that works in the complexity of the building space. So I just want to introduce you to kind of this cluster of concepts that comes out of the social science field, right? So there's something that's called collective intelligence. The collective intelligence is like Ashrae, right? The body of collected knowledge in your field that gives you a trained kind of worldview, like this is how the world works. We need to partner that with something that's called collaborative intelligence. This is like the emotional intelligence that you sometimes hear about, which is like reading other people, but in a collaborative sort of group setting, right? So, you know, how do people set up groups and relationships such that they want to cooperate with each other, even though they're coming from different knowledge bases? How do we get the best out of the synergy of that diversity of ways of looking at the world and their worldviews so that we create together what's known as co-intelligence, right? So this is co-creative cultures that seeks solutions to common challenges, right? That we bring our best to sort of a common vision. Now, the other thing that I talk about a lot is that design, right? I said that BIM models are not design. They are the artifacts of our thoughts. Design is about the social construct that creates a common vision of a future object that incorporates all of those necessary worldviews, right? So it is an act of collective imagination. That is what design is. And sometimes we use BIM models or sketches or other things in order to get the things out of our you know, narrow worldview mind into public discourse, right? And we have a graphical language that we use together that's been developed over, you know, multiple hundreds of years and now is represented in our BIM models in a different way than it has historically been done with elevations and sections and plans and yada, yada, right? But it's all about getting what's in our imagination, what's locked up in our brains, into some public space where other people can see it too. And I also, back in the before times, right, I would always encourage people to share the pen, right? And this sort of dynamic of being in a room with other people and drawing things together on a piece of paper or drawing things up on a whiteboard. I know it makes me old school, but historically, you know, very famous architects have seen that the act of, literally the act of physically drawing is useful to the thinking process. And so for those, any of you who have like kids who are kinesthetic learners, right, they have to be doing something in order to get information to embed. Well, throughout the history of our industry, historically, you know, how much, yeah, he was a famous architect. He said, for me, drawing generates thinking and vice versa. For Le Corbusier, he was a famous architect from the 1920s, basically the inventor of modernism and architecture. He says, I prefer drawing to talking because drawing is faster and it leaves less room for lies, right? Like we can't convince ourselves of a thing that can't actually physically work. Just because we thought it might work in our head. And then Norman Foster, he's a little bit more modern. He just passed away, but like his heyday was, you know, 1980s, 1990s, early 2000s. He said the pencil and computer are, if left to their own devices, equally dumb and only as good as the person driving them, right? And that's that old sort of computer science adage, garbage in, garbage out. It's the same for design. And so that's why we have to have these ways to reveal what our thinking is to other people, to see it might be a good idea, but only in a very narrow context. And it's kind of garbage once we have to put it into the whole ecosystem of all of the disciplines. And so the move, right, for those of us who've been super trained into a super narrow way of looking at the world, is to move from the question, do you see what I see, to help me see how you see it, right? And when we're able to ask those questions sort of in both directions, that's really where we can start to build this design empathy and kind of move forward. So let me give you an example. This is I used to run a training program where I was trying to encourage people to develop some more sort of client-facing skills, right? And so one of the exercises that I asked was, okay, so we're kicking off a project. First time you've met folks, and the architect is just, said a little bit about the project, and we get the opportunity to ask 20 questions, just like you do with little kids, right? And so I asked everybody, okay, So what's going to be your first question? And every single time I ran this course, and this even happened on a real project like 2 days ago, the first thing out of the gate is, where are the civil connections for utilities? Inevitably, plumbing engineer, earnest plumbing engineer is going to raise their hand and ask where the utilities are. And I would always push back. And you have the benefit of already having me blather on about design empathy. And I push back and I say, is that the best and highest quality question to ask when building a relationship that shows that you're ready to be a partner, right? What are the kinds of questions that we should be considering? Are they questions about vision? Because anything that's in our imagination about design has to be contingent on the architect's imagination about design. You know, is it about aspiration? Is it about goals? Is it about priorities? Is it about anything but where are the utility connections? And so I just encourage us to think about that. You know, when we have that seat at the table, how are we going to use it to build relationship? How are we going to use it to stay aligned with that collective vision that we're all trying to build together straight from the start? Because I think we need to understand that, you know, kind of there is a difference between just coordination and sort of a more integrative approach to design, right? So there's always sort of physical integration, which is literally coordination. And all of us have lived this. People trying to pack too much into super tiny ceilings. There's not enough room, and you say, I need access space, and you say, no, there's an NEC code that means that you need to leave me a space that's 36. Nobody is respecting us. You kind of have to feel like you're a little bit boxing there. Like, no, like you always got to push back, right? And I swear to God, every time you get a new set of backgrounds from an architect, it's like everything you previously coordinated has disappeared out of convenience to somebody else, right? Or you get that space that's trapped behind a stair core and an elevator core and a toilet core, like, and you just can't get out. I mean, look, we've all lived it, right? Anybody who's ever been in design, we've all lived it, right? And so we have to get good at coordination, and some of that we do in BIM models, you know, and sometimes, you know, we keep going over back and back and back, and we're able to structure things, maybe take a little bit of unique approach. This was an interstitial floor that we had above a bunch of animal holding facilities at a biology sort of lab space at a university. And, you know, we kept, you know, looking at, you know, how you could walk down this corridor and kind of, you know, reach through in order to address, you know, we had air valves that were on either side in the vertical, so you could basically reach and, you know, basically get them out when you need to get them out, or change actuators or whatnot. But it took a really long time for us to figure out how to do this so that you would never have to enter any of those animal rooms in order to do the servicing on the project, keep everything uptime and live. Now, you know, and then the other thing that we need to think about when we're thinking about sort of physical coordination is, you know, sort of the aesthetics. So this is just a story. This was at the Los Angeles County Museum of Art. Most of our air handlers are in this internal space that you see right here in the middle. There's a nice big louver in front of them. Nobody can see them. But we had two air handlers that were up on the roof, and the architect was like, you know, he was complaining to me. He really wanted to show this fan, which you can only see from a couple of angles, to show like that's the working heart of the building, even though it's just one out of like 6 air handlers in the whole building. There's a whole chiller plant somewhere else, but he's like, no, that's going to show like this is the engine of the building. And so he was perfectly happy to see that. But then when we were doing the final walkthrough, we were up on that roof, and he's like, Erin, you know, and you can see like the air handler is like super far back. This is just the relief fan. You know, he's like, Erin, the gaps between the panels on the air handler, I mean, they're so big. And I'm like, well, I mean, they're bolted and then they're cocked. I mean, nobody's going to see them. And he said to me, Erin, God will see them. And I was like, I don't think God cares about the air handlers here. But it was something that he really cared about, even though nobody would ever see it. Like on this project, we had done it's kind of so much work with 3D. This was like way back in like 2000, 2002. I mean, this was like, you know, embryonic BIM capability. And I remember, like, you know, we were working with the structural engineers on how we're going to handle all this piping and get all these ducts through these braces, and you know, and we had to have just the right diameter to be able to get it through those triangular bases and those triangular braces. And I was even just joking with my my structural colleague just the other day, and he said, yeah, my wife, she said during those times, sometimes I would wake up in the middle of the night, or not wake up in the middle of the night, but just be blathering about, you know, it's the diameter. It's the diameter versus the whatever, you know, kind of whatever his distance was. So, you know, these things get in our head when we really try to find these multidisciplinary solutions that, you know, in this case, we're trying to preserve, you know, clear height for all the big artwork that was coming through. But that was really kind of physical coordination, right? Which obviously is capable to do out of, you know, BIM models. Then when we look at visual, you know, a lot of times in our space, this is Lloyd's of London. Sometimes people want to expose our services, you know, which just, you know, makes dimensional control and control over additional finishes even harder. You know, we had a project, again, in sort of Beverly Hills, which was for Prada Beverly Hills, and they wanted everything to seem sort of seamless. I mean, the first thing that they wanted was they didn't even want a front door. There's actually a 44-foot wide piece of wall that lowered into the ground every morning, and then we basically had a 44-foot long air curtain that you know, that would basically function as the wall. But inside the building, we had an all glass roof. What you can see here on the right hand side is that all glass roof. The only single piece of equipment we were allowed to have on that roof was one condensing unit for the emergency backup for the IT room. Everything else basically built into the little building on Rodeo Drive. And so, you know, we really had to be clever. So we worked with the structural engineers, and they came up with these sort of box beam solutions that allowed us to run all the sprinkler piping and some of the wiring for the fire alarm services in the beam itself, as well as power. So we basically felt like you were screwing in some of these lighting fixtures into the beam itself, but it was basically, there was a back box that was already built into the back side of the beam before they welded it up that could basically take that connection. And then along this back wall, you can see we've got these punka louvers basically built in to this mirrored wall above these support services that hold all of the clothing, the storage for the clothing, so that you have this kind of seamless approach that doesn't scream like, you know, I'm a mechanical engineering piece of equipment, but is kind of integrated into the aesthetic that the architect was looking for. And so there's a lot of work that we all have to do all the time in order to please our architects with regards to visual coordination and integration. And so last but not least, I just want to kind of bring us into the realm of performance, because I think that's the one that kind of really gets us going. So there's this one example that we have, which was for sort of the Caltrans project. This is the California Department of Transportation. And they were interested in a high performance building, you know, back about 15 years ago. And one of the things that we were just starting to do is starting to integrate photovoltaics into our designs and trying to figure out sort of cost-effective solutions that didn't feel like you were sort of double paying for everything. Because, yeah, it's easy to put PV up on the roof, you know, and maybe it's even more efficient to put it up on the roof, but then you get single duty out of it. And we were really trying to push the envelope and see, how do you get a twofer, right? How do you get 2 for 1? And so we played on the southern side of the building with actually using these crystalline type PVs in order to actually act as our shading devices, so that at the same times where you would want to be controlling the sun coming into the building from a human comfort point of view, well, you might as well collect all of that up and use it as you know, sort of energy generation for those times, because it's likely to be those times where you kind of are wanting free electricity to drive your cooling plant. And then around on the other sides of the building, where we didn't have sort of that really heavy heat load on the east and the west, we had these vertical scrims with pieces that could open up. So when the sun was on your side of the building, you had these perforated shades. When the sun moved around to the other side of the building, you could open it up and be able to see all of downtown Los Angeles. So again, looking for those twofers with those other disciplines, we had to bring the facades folks into that one to figure out how we could weave all of the conduit back down for all of the PV. And then all of those outdoor actuators were all facade devices that actually were controlled by the BMS. So I want to then move into this question of sort of cascading wisdom throughout the project, right? And when we think about ourselves as sort of multidisciplinary teams that are trying to understand things, between every pair of team members, there's kind of a set of interfaces where you have to play together. And so we actually have a process within our firm where we have some master coordination checklists, that are cross-referenced by phase, and people kind of sit down together and say, well, let's just run through the checklist. Let's make sure that we're not leaving something to the side just through oversight, right? And sometimes we have to navigate, multilateral agreements, just like some kind of international treaty sometimes to see who gets predominance in sort of their preferences taking the lead. And I'm sure all of you have dealt with that as well. So when we talk about from a performative aspect as well, we also have to talk about, kind of performance aspects related to uptime, right? And this is often where we're kind of interfacing with the electrical and IT, maybe even the AV folks, about, trying to preserve mission in a property. So you see this a lot in data centers. I'm just going to give this example of sort of a very unique data center experience that we had. This was for Stevens Hall, which is at University of California, and University of Southern California, excuse me, at their health science campus. And so this is kind of what the end product looks like. Just to give you some context of what's going on there, sort of all of these colorful lights down here are LED lights that are linked into the data center, the server farm that's actually down here. There's 48 racks that process brain imagery. So this is like a neurosciences lab. And then up in these kind of double height orangey spaces, there is what's called a digital immersive visualization environment, or the DIVE is what we ended up calling it. And they have a gigantic 4K high definition screen that basically allows those brain images to be transmitted up onto the screen. And basically the researchers can kind of literally digitally walk through the brain. They're doing a lot of research here about trying to solve Alzheimer's and other sort of neurological disorders. And so this has given them a way to scan brains of live patients, be able to kind of literally walk through their brains to look at different structures and collect information that they couldn't collect otherwise from live patients. And so they're right next to the hospital, and so they have a couple of MRIs that serve clinical purposes and then double as research purposes. So that's the project. It was built into a building from the 1950s. It was originally the original administrative office building for the hospital. The floor heights were like less than 12 feet floor to floor. The thickness of the slabs was like 3 inches. It would never pass current seismic codes. It hadn't been touched in about 20 years by the time we got activated to do work in it, because A, it was historically protected, and B, it had gotten damaged in the 1990s in one of the earthquakes. But they really wanted to attract this researcher. They said, we have a whole building you can have, and we'll raise money for you to go into it. And so that's kind of where we ended up. And so really it was a question of, how do we work together to allow for the seismic strengthening of the columns, not put too much load onto the slabs. And then the greatest issue that we had is that the campus said, we don't have any more chill water for you. We can't guarantee chill water under all circumstances. So you kind of need to put in your own plant. And we're like, okay, it's a teeny tiny little building. I mean, we only built out like 25,000 square feet, and there's two more floors that could get built out into the future as they expand. but they really wanted to kind of upgrade it to look modern, to reflect the technology that we were looking for, have modern spaces that the students, the researchers, and quite frankly, the donors would be willing to come into and keep sort of pumping money into this very important kind of research. So up top, we have, we're allowed to connect to the central plant whenever they do have capacity. Otherwise, we have a couple of chillers as sort of backup up there, and water-cooled chillers, and then we have an air-cooled chiller that takes care of the data center when we're on emergency power. And, you know, as with all of us, you know, we had good diagrams, we had, you know, BIM models, but the crux of this entire problem was, and this is, you can kind of see here how the server farm downstairs, which the researcher really wanted these LED lights to be able to flash on and off to tell people who are walking on the street outside how active all the research was due to the processing that was going on in these server farms. And what we learned, you know, and this is that giant screen that's up in the dive. What we learned is that these processing procedures are so intense that if they're ever kind of stopped in an uncontrolled manner, they basically have to start all over again at the level of detail that they're looking at. And so this formed kind of one of our greatest design challenges. We had this 48 rack server farm that was down in the basement, basically. And the campus had a history of short power outages, and we had a super tight site that limited our generator capacity to only 800 kVA, which basically meant that you know, we could only run 10 racks on that emergency generator and the air-cooled chiller that was going to support it. And they told us how much cost there was for having disruptions associated with data processing. They couldn't afford for the servers to get above 120 degrees or they'd start to have a meltdown. And we said, well, we don't have enough space for that. You know, there's literally no way for us to put a bigger emergency generator in there. And so we basically had to add UPSs for running 38 of the non-core racks long enough for them to migrate data processing of their most critical solutions into the 10 core racks. Then we had 9 minutes of UPS in the 10 core racks for them to shut down if the cooling wasn't available. And then last but not least, you know, the mechanical problem was as soon as we lose power, we lose everything, right? That the chiller plant was too large to run on that emergency generator. And on our air-cooled chiller, it took us 6 minutes to get up to full capacity. So what are we going to do in that 6 minutes? And so this is where it's kind of the performative aspect comes into play. You know, what we saw in the first case, we thought, oh, well, we'll just put in some crack units. We'll just open up all the doors automatically and put in some crack units. But that didn't keep us below 20 degrees because, again, you know, the air-cooled chiller couldn't get up to speed fast enough, and we didn't have enough thermal mass in the slug that's in the piping in order to keep up with it. We said, okay, we'll put in another crack unit. It's like, and that's not enough. So in the end of the day, what we realized is we had to store our own chill water capacity every day in order to have a reserve capable of covering us for those 6 minutes while all of that migration was going on. And so the simplest solution was actually to put in a 700, because we had in-row cooling. So all we needed to do was have a source of cold water and pumping, which was a really, really low temperature. You know, really low amounts of kilowatts that we were imposing onto the generator. So that's, and then the client said, well, I'll just keep the cracks in there just in case, you know, because we could always open up the doors and get a little bit of air movement going on, as well as kind of pumping the in-row coils with this pre-reserved 750 gallons of chill water. So that's, again, you know, it was a lot of conversations to get to the bottom of that. And then we had like 8 different emergency failure modes. What if the air-cooled chiller fails? What if the pump fails? What if the da-da-da, you know, we went through everything related to redundancy. And then we actually had, we wrote commissioning specs in order to test all of it to the satisfaction of the university. But it took us talking to the researchers IT guy, every single discipline in order to get sort of that optimum approach to keep that uptime for them for what they felt was most critical. That's that design empathy and that co-intelligence where everybody was at the table. And just a couple more examples here. So large volume spaces, we had the opportunity to work with a client that took the old kind of Spruce Goose hangar where the Spruce Goose airplane was built back during World War II. And so that's a picture of kind of what it looked like then. And our client basically took it over and renovated it to put a 4-story office building inside the hangar. The hangar is historically protected because it is an all wood building, because obviously during the war, all of the metal was going to the airplanes or the ships, right? It wasn't generally available. And so this is a completely wood glulam structure that has been protected by the Army Corps of Engineers for a number of years. And so we had to understand, how can you build a 4-story building inside of a hangar, meet all the current fire codes, and make it a functional space. So part of our solution was that, we had to hold all of our new construction off of the walls so that the new construction didn't end up being sort of a cause of fire that would basically burn down the existing building. So I had to put a gap in there that you saw between the occupied space and the existing wall. Then we had to do a bunch of timed egress and smoke control analysis with our fire engineers in order to look at, once we turn on all of those smoke exhaust fans for smoke control system, how long does it take for people to get off of the 4th floor down through the building and out? Because this is a giant double hangar that's 750 foot long. This is a gigantic smoke control system that we had in that space. Similarly, from a daylighting point of view, the entire facade was protected, and those big pieces of glass that you saw on the previous slide, those were all single pane glass. And according to the historic preservation order, all of the glass had to remain or be replaced with in-kind single pane glass. So that gave us great daylighting, but we had to have controls on shading for glare when the angles were too low, and also from a comfort point of view. And then from an acoustics point of view, you can imagine when you have a 750 foot long atrium, that any noise that's created down in the lower level is going to bounce all over the space and adversely affect the concentration areas that where people were actually working, because we had all these amenity spaces on the ground floor and concrete floor, so everything is just going to bounce all around. And so what the acoustics engineer did was they worked with the architect in order to put all of the sealed conference room spaces on the edges to be like a buffer. So all of the conference rooms for the offices were all on the edges right above where all those downstairs meeting spaces were, so that they acted as kind of a shield, and that the actual high concentration areas in the open plan office spaces were a little deeper in order to control noise. I mean, we always see this kind of sort of multidisciplinary coordination at facades, right? Like we're always trying to understand the thermal performance of the facade elements, whether it be glass, or how do we get sort of daylighting into the space. And so, sometimes we've kind of mapped this sort of expectation versus reality with regards to the design process, right? We've all got tools where we can see kind of what the incident solar radiation is on the outside of the building, but then we have a bazillion other tools to tell us what's going on inside the building. You got your lighting people do daylighting analysis there. You got your energy modelers over there. You got the people doing your thermal comfort analysis over there. And everybody's trying to figure out how much this is costing. You got your acoustical engineers trying to figure out what the break-in is from outside. Everybody's working in all of these different models in their own silos, digital silos even, in order to try to represent what the world looks like, and trying to get convergence on what the actual sort of multivariate performance is just inside a facade is something that we've all been chasing for a very long time. And so it takes that design empathy, it takes that dialogue that's grounded in the analytics in order to find these solutions together. And we see that now in the context of carbon, right? We're all getting up to speed on decarbonization efforts and the decarbonization task force from Ashrae. And the paradigm shift for us is to think about more than just operational carbon and energy efficiency into sort of a whole life carbon analysis. And what a whole life carbon analysis says is that the carbon that's emitted from our design choices is not just in use operational carbon, but it is also all of the embodied carbon that comes with the materials that we specify and that we install during construction, and then when we reinstall them periodically when the equipment gets to the end of life and has to be demolished in some way. And so the paradigm shift that we really need to be keeping in mind is whole life carbon assessment. And what you see on the screen right now is sort of the global understanding of how we report by building stages, from products to construction to use to end of life, and then by sort of high-level system components, right? And we would fall, amongst others, into that services category of reporting. And what we know, just like we saw before with that curve, that McConahey curve on the upper side, right? So we've always been familiar with that operational carbon, that our ability to reduce operational carbon gets lower and lower and lower the later we are in the project, except for maybe a little bump in commissioning. It's kind of the same thing, but in reverse. You can imagine that zero line being a mirror, that our ability to influence embodied carbon is drastically reduced as we get later and later as well. So it's very important for us to do early phase calculations to not only understand operational carbon, but also the embodied carbon of our products, and for us to be engaging more with the manufacturing community in order to have what are known as environmental product declarations, or EPDs, available to all of us in order to make those good judgment calls with our clients about how to reduce their carbon footprint going forward. So again, like I said before, design is about creating a common vision of that future object that incorporates all worldviews. We are the advocates for mechanical engineering needs. And when we come to that with design empathy, share our knowledge through the tools that we have, and really kind of approach collaboration with that sort of iterative mindset where we're trying to come to something that incorporates all worldviews. It's an active social imagination as to kind of what world we will create. And that is the question for all design professionals in this day, especially with carbon being such an important thing. What world will we imagine together? So that's what I had to talk with you about today. I will take my screen off and take questions. Thank you very much.
Hi, Erin. I threw a question in chat, but I was curious, for that server room, what was the 120 degrees in ambient temperature, or is that an actual, like, inside the server rack or cabinet temperature?
Inside the rack is what they were looking for. Yeah. Yeah. So I guess people could just come off mute as well if you just want to ask them directly. You don't have to type everything. Okay. So Sam, do you want to take it back to wrap things up?
Yeah, I just have one question on that hanger for the spruce goose.
Yeah.
Is that actually in an airport somewhere, or is that somewhere?
No, that's the hangar where they built them. So it's slightly north of LAX, the Los Angeles International Airport. It's on the old Hughes aircraft property. So their manufacturing facility was just north of the airport, and now is in kind of a residential and up and coming sort of commercial area.
Cool. All right, if anybody has any questions, you can unmute. If not, then hang on for another minute or so.